Hello, my name is Joachim Eldén, and I will give a short introduction to research that we did at KTH with the purpose of looking at robust ways of learning the behavior of systems that change dynamically over time. And this research is done within the Assemble project with funding from the Swedish Foundation for Strategic Research. To model dynamical systems, we make use of state space models, where a sequence of system states describe the evolution of the system over time, and where a sequence of measurements describe the observations of the system. The states can represent physical quantities such as angles, velocities, or positions, and the observations are, for the purpose of this illustration, represented as images of the system, but could really be any type of measurement. To learn the behavior of the system, we introduce probabilistic rules that describe how states evolve over time and how the observations relate to those states. These rules are parameterized by a parameter theta that models our uncertainty of the system, and the goal is to learn this parameter from a sequence of observations. Dynamical state space models are widely used to describe systems ranging from, for example, autonomous robots or vehicles to biological systems, and devising methods for learning the parameters and behavior of such systems have wide applicability. One way to define what it means to learn the parameters is to select them such that observations appear as likely as possible. It is, however, often difficult to compute how likely a sequence of observations are, as we don't know the states a priori. A solution to this conundrum is to look at how likely the joint set of observations and states are, which, for reasons I will not go into here, is frequently easier to calculate. But since we don't actually know the states, we remove the explicit dependence on the states by averaging over all possible state sequences. Updating our assumptions about the parameters by maximizing the average or expected likelihood leads to an iterative refinement of our knowledge known as the expectation maximization algorithm, or simply the EM algorithm. Still, even for moderately complicated systems, computing the expectation and maximizing it is often difficult, so we'll rely on approximations. And we can depict the process of finding the optimal parameters to that of maximizing the likelihood given local approximations. For an initial estimate of the parameter, we find the local approximate expression of the likelihood, we find the maximum of the approximation, and then we update the estimate and repeat. If our initial estimate of the parameters is sufficiently close to the optimum, this procedure can be shown to converge towards that optimum. However, if the initial estimate is far away, one can obtain an approximation that is not well behaved and that may not even have a well-defined maxima, even if it's a good local approximation. The purpose of our work is to look at methods that ensure that the approximated functions will always be well behaved, leading to so-called damped optimization methods, or methods capable of describing over what parameter range the approximation is accurate, leading to so-called trust region optimization methods. The full details, along with further application examples, can be found in a publication that was presented at the 2018 International Conference on Information Fusion. Thank you for listening.